So this talk is based on a rather simple idea. So let's see. So first thing to talk about is Hoc Shared Homology. So we have to look at how it's defined. So suppose K is a commutative ground ring and A is a not necessarily commutative K algebra, and we will be taking, and whenever we'll say tensor, we'll be taking tensor products over K. So that's the general instructions. Now given an A bimodule M, we set CNAM as M tensor A tensor power n, and then we define these three kinds of maps, these degeneracy maps of so an object in CNAM, naturally it looks like something like this. Remember that the tensor powers are taken over K, so we can't really put the term here. So I have three kinds of degeneracy maps. So the first, zero degeneracy, just multiply. So what we'll do is we'll just at each degeneracy just takes two consecutive elements and puts them together. So the first one just takes M A1 A2 AN, and then when you're doing the ith one, d ith, you just go to the ith position, remove the tensor sign, just put this, and go to AN. And how do we get the last degeneracy? We just take the AN, turn it around and put it in front of M. So that's why we require M to be a bimodule. Is that written? Yes. So A is a bimodule. So M is an A bimodule. So these are the three. So these are the degeneracy maps. So the first one. So we're just taking the consecutive ones, putting them together, and at the last one we just circle it around and bring it to this side. So now if you consider the alternating sum of these maps. So this is basically a simplicial complex. So if I take the alternating sum of these two maps, then I will see that this is a differential actually. I can get that composition to be 0, and then we will say that Hochschild homology, by definition, Hochschild homology will be simply the homology of that complex. So, and we will define Hochschild homology by HHN. So that's Hn of C star AM comma B, where B is the differential. So in particular we could take M to be the bimodule A itself, and in that case we say that HHN is the Hochschild homology of the ring. So this is the basic construction for Hochschild homology. So Hochschild homology is kind of the first step towards going towards cyclic homology, which actually plays the role of Dirham cohomology sort of object in non-commutative geometry. So the important point here is that that A is not necessarily commutative. Now what you can see over here is actually, not see over here, what you can actually prove is that if A is a smooth and commutative algebra, so this is the idea, if A is a smooth and commutative algebra, this is actually the same thing as the modular differentials. So in effect, when A is non-commutative, I can actually think of this as the starting point of non-commutative differentials. So this is a very important object, sir. So this is sort of the starting point of Dirham theory in non-commutative geometry. But that is not exactly what we are going to do. So what we are actually thinking about here is, so our question is, can I define the Hochschild homology not just of a ring, but can I define the Hochschild homology of a module? So this is not really Hochschild, this is kind of the Hochschild homology of the module of the ring with coefficients in the module. But I am asking, what if I wanted to define something like the Hochschild homology of the module itself? That's what I always wanted to define, and actually what I really wanted to define was that of line bundles. But anyway, so something I always wanted to define was how to define the Hochschild homology of a module. But this, as you can see, makes no sense. That is, if I had M tensor M, M1, M2, M3, there is no way to really to multiply them and say this is M1, M2 tensor M3. This doesn't make sense. So what I want to do is sort of define something like HHN of M, and more generally that of a sheaf, and in particular an invertible sheaf would be a line bundle. So that's okay. So it's not immediately clear how one could define the Hochschild homology for a module M over a.
If the ring can be non-commutative, how do you define the module over a non-commutative?
It's a bimodule, I said.
Sorry. How do you define a sheaf over the spec or?
No. We will be talking about sheaves over a Grothendieck site.
Over
a Grothendieck. Yes, over a site. Over a site. So the question is, we want to define Hoc Shared Homology. More precisely, I am saying as for a separated pre-sheaf on a cloth entity. We will describe what each and those things means. So it is not immediately clear, as I said, how to define the Hoc Shared Homology for a module over a ring. Or more generally, we want to define the Hoc Shared Homology of a sheaf on a general Grothendieck topology. And indeed, even if, I mean, here it's a module, so it's already an abelian group. But I wanted to define it even so generally that this would even work even if it was a sheaf of sets. So there I wouldn't even have a abelian group structure, let alone multiplication. So how do we define something like that? So, and as I said, this is distinct from what you might call Hoc Shared Homology of a scheme with coefficients in the sheaf. That's completely different. That, if you have a structure sheaf like this, XOX, then all you have to do is, and you have a sheaf over that, some F, then all you have to do is define this complex F tensor OX tensor N. You have B and you take its hypercohomology, and then you will get Hoc Shared Homology. So that's what Weibel has done. It's already, so it's quite well known. So it's very old, in fact, 1996, as you can see.
So is this your construction going to be some generalization of this construction?
No, it's completely unrelated. Completely different. So what we will actually do is what we will do is we sort of restate a sheaf. So we will understand a sheaf as not just, so what is a sheaf? A sheaf to start with is a functor on a category with certain properties. But what we will do is we will understand a sheaf as a category in itself. And once I understand a sheaf as a category in itself, I can take the nerve of that category, which is a simplicial set, and then its homology groups, I will define them to be Hoc Shared Homology. So that is the idea. But so in what sense is a sheaf a category? It's actually not just a category, but a fibered category. So here if you read that, there's no way to understand that and without a diagram. So this is a definition from SGA1 rather. So what is a fibered category? A fibered category is basically something in which there are pullbacks. So what does that mean? So what that means is, so let's see. So suppose I have this. I have a functor between these two categories. So what do I mean by this category F is fibered over this category C? What it means is that, so to start with, you have to talk about what is a Cartesian morphism. So suppose I have these objects xi to eta. So this part is in F. So this thing is inside F, and this is sitting over P xi to P eta. So this is some phi, and this is P of phi. So suppose I have something like this. So I will say this is Cartesian over this if given some xi prime, which maps here. But suppose xi prime xi prime may or may not factor through this. But suppose that xi prime downstairs, if I went here, P of xi prime, then I would have this map, and suppose that factors through the here. Then there exists a unique factoring here. So the idea of a fibered category is if it factors on top, factors down below, then it factors on top. So this is when we will say that phi is Cartesian. So we will say phi Cartesian over P phi. And what will we say when what is a fibered category? So a fibered category is that which, so suppose I choose any morphism here, I choose some morphism here, F from U to V inside C, and I choose any object eta, which is any object eta inside F sitting over it. So this is just P, and then there will exist a Cartesian morphism. Then I can find some xi which sits over U, and this is Cartesian. Note that we do not assume any uniqueness in choices. There just exists a xi on top. But this is of course assumed to be unique, and this is very important. And so the thing is that, so given any morphism, so I take something that sits over the target, and then there is something Cartesian mapping to it. It's not true in the opposite direction. If I choose something on the source, it's not true. So this is what we need. So this is what we say is a fibered category. Now we say that the fibered category is fibered in sets if the the fiber over each object is basically so the fiber over each category is a set. So the collection of those objects is a set. So basically, so as we said before, a fibered category is something in which you essentially have pullbacks. What does that mean? So this is exactly what it means to have a pullback. So suppose I have for instance, I have a vector bundle, for instance. So I take the category of vector bundle. Suppose this is a topological space. On V, so you consider all the objects that map to V. So that's a category. Now, once I take any map F from U to V, then I can take any element of the category which sits over V, and then this gives me an element here, up to isomorphism. So that is exactly what it means to say. So suppose the category of objects over eta is F eta. Then given this morphism F from U to V, I naturally get a functor from F eta to objects, F sitting over V rather. So I get a functor from FV to FU, and this functor I call F star, right? And we also have the obvious property that GF star is F star G star. So essentially a Fibred category is a situation which allows me to have a decent notion of pullbacks. So this is what we say is a Fibred category. And if the objects on top are Fibred are sets, are small categories that is, then we say that this is Fibred in sets. But now then there is a starting point. So there is a one-to-one correspondence between pre-sheaves of sets on a category and the categories Fibred in sets over C. There is actually a one-to-one correspondence. So the one-to-one correspondence is actually very easy to form. So suppose I have any category C, and a pre-sheaf F. So the category below is obviously the category C, and what is on top of the category C? So how is the new category means F defined? So this is already the pre-sheaf F. So maybe we'll make it this. So how do I define this? So the objects in this here are objects are just U comma xi, where xi is simply an element of F of U. And what would be a morphism here? A morphism from F from U to U xi to V some xi prime would be a map, something from, it would be a map from V to U, which takes xi prime and maps it back to xi. So that would be a morphism over there. So that is how, given a pre-sheaf, I can construct a Fibred category, and you can show that it's quite easy to see that you can reverse the construction and prove that there is a one-to-one correspondence. So now we know that given a pre-sheaf, I can get a Fibred category, and given a Fibred category, I can get a pre-sheaf. Fibred in sets. So this allows us to interpret a pre-sheaf as a category by itself, as opposed to just a functor on a category, and hence we will work with a simplicial object that will now map to the nerve of C. So now we have something Fibred over C. So how do we work with the nerve of the Fibred category? It will be over the nerve of C. So now we have to be more careful, because we are not just considering pre-sheaves over a category, we have to consider sheaves over a site. So suppose that I have a small site, C tau, and so cov tau U is the set of tau coverings of U. And so now I define a new category like this. So I define a category cov tau of C, so that's written over there. So the objects of these are all the covers in all the all the coverings of all the objects as U varies over the objects. Now given a cover, now there would be a morphism of covers. Given a cover U of U and a cover V of V, then a morphism like that would consist of a triple which says that there is a map on the sets which it's covering, F from V to U, and then there is a map on the upper objects over there, such that we always have. So basically it means that what is a morphism of covering? So I have a cover of U and it maps to any of its pullbacks over V. So that's what I'm saying. So that this would be all Cartesian squares. So basically that would be a morphism of covers, a cover of U pulled back to a cover of V. So that's what I mean. So, and it's clear that you have an obvious functor from cov tau C to C, which just carries the coverings of U to U. So now a section of P tau will be just a functor which has the obvious property that P operation S is identity. So now here you have a slight, you can ask a philosophical question that it is always bad manners to say that two functors are equal. One should always talk about two functors being isomorphic. But the thing is that as we will go on to the next slide, we will see that for sections itself, the thing is that we have sufficient examples. So it's not like it's really restrictive. because I mean somebody asked me this question in Vanderbilt that it's not a good idea to ever say. So examples of sections. So what could be an example of a section? So I have coverings of objects of C down to C. Obvious example of section is that which takes the object to its trivial cover. That's one example. But there are other much more interesting examples. So for instance, now suppose I take I think that is a small et al site, right? Small et al. Yes. So pull back and so what I do is, given that it's over X, so choose an et al cover of X and just use the et al cover of X and pull it back to all the objects, and you have et al covers for each object. So that's obviously what you mean by a section, right? So that's one way. Or you could define something. So this is something I saw in Milne for the first time. That is, if you already have a cover, you can use it to define a sort of an et al site of the cover. In what sense? That you take your objects not to be maps that go to et al maps to X, but which factor through something in that cover. And you can take a morphism to be an X morphism from U to V, and then families of joint lists. So once again, the thing is that you choose another cover, and you use that cover to to pull back to covers of each and every object. So one of the points here is that we choose the fiber products in advance. So there is a question of choices involved here. That is, we choose the fiber products in advance, and they have the corresponding maps between them because they are fiber products. So the thing is that the fiber products have to be chosen in advance. They are not chosen at a later point. So once we have chosen, they are fixed. And similarly, we can define similar sections in this exact same way for pretty much any other site. Just choose a cover and pull it back. So those are to show that the collection of sections is sort of non-empty. So now we are coming to the simplicial Abelian group. So F is a separated presheaf of Abelian groups on that. So we will mention what is a separated presheaf. So a separated presheaf that is so given U. So I mean U and two sections, separate presheaf F, say, and sections S and T belonging to F of U. Suppose that I can find a cover. Suppose there exists cover. There exists cover UI of U such that S restricted to UI is actually T restricted to UI. Then S equals to T. So actually, all the presheaves we could possibly think of are really separated, but this is a technical condition. So the way to so how do we sheafify something? So to an open set, we associate all the elements on the covers which map to the same point. But actually doing that will not give you a sheaf. That will actually give you a separated presheaf. If you do that operation once more, if you do that twice, then you'll get a sheaf. So the thing is, so this is a very important condition. So to have separated presheaves. So suppose that we have a separated presheaf of Abelian groups on C. So first we are starting with the sheaves of Abelian groups. We'll come to sheaves of sets. But so that will be almost the same thing. But anyway, so F is a separated presheaf of Abelian groups, and now given a cover of U, we just set FU to be these objects. That is, xi belonging to FUI, such that they restrict to the same thing on the intersections. So that's what I will mean by F of U. And using this, as you can see, F becomes a presheaf on curve tau C, because now it's acting on the covers rather than on the objects. So suppose I have a section like this, then I set Fs of U equals F of SU, and then Fs becomes a presheaf on C. As I said before, F is already a presheaf on curve tau C, so F of SU makes sense now. So Fs becomes a presheaf on C. And now, as you might remember, the nerve of a category is a simplicial set which looks like this. So the nerve of nerve in C of a category, nerve in C of a category, it consists of these simplicial objects. So an n simplex here looks like F0 Fn minus 1 Un. So how are the degeneracies defined? So the zeroth degeneracy is defined simply by bringing, so sort of forgetting, so dropping the Well, no, the zeroth one is done by simply dropping the U0.
I think degeneracy there should be extending, so like for instance.
Oh, yes. I always make the face maps. Yes, of course, I'm talking about face maps. Yes, so dropping the U0s, then each at the zeroth level you just drop that element. So this is the nerve of the category C, and it's obvious that this is a simplicial set. So this is what we have as the nerve. So now, as I said before, we will define a simplicial Abelian group that sits over the nerve. So corresponding to each n simplex, I will define something that will give me a simplicial object. So we have a simplicial Abelian group SF of S. I mean, with respect to a given section. So S should be remembered. S is a given section. So SFS I can define whose n simplices are simply U0, U1, UN, Fn. So lying in NCN, and it's just Fs of UN, the last one. So let's go back to the previous one. So given any U, I have already defined Fs of U, and now suppose I choose an n simplex like that, and then the term corresponding to it on top is simply Fs of UN, the last one. So all the face maps, as you can see, are as you can see, all the ones before n are all easy. You just forget that part in the simplex. And how do you get rid of and when you drop the UN, when you are doing the last face map over there, you just pull back that element from Fs UN, just pull it back to Fs UN minus 1. So only the last face map is sort of easy. It gives us something to think about. So we have so that allows us to construct all these. This gives us the 3 face maps. So we have the face maps, and the degeneracies, of course, are trivial objects. They are just done by putting in identity maps. So there's nothing to think about there. So the only thing to think about is that when you have Fs UN, if you are dropping any object other than UN, you don't need to bother about it. But when you are dropping the last one, just pull back that element to Fs UN minus 1. So that gives me a simplicial Abelian group, and everybody can see where this is going. So we have the Hochschild homology of the presheaf F with respect to S is simply the homology of the simplicial Abelian group. So that is our main definition. Now, properties. So for any two sections S and S prime of this functor p tau from cov tau C to C, S prime we will say is a refinement of S if each S prime U is a refinement of S of U. So S is a section of the coverings. So we will say that one section is a refinement of another section if at each point the cover obtained is a refinement of the other cover. So now, with a simple construction on fiber products, you can prove that obviously if you have 2 sections, then there is a section which is smaller than both. Just like any 2 covers have a common refinement. So that's what we are saying. So you can just construct using fiber products. It's a very easy construction. Now suppose that F was not just a presheaf but also a sheaf. Then for any 2 sections, you're going to have the exact same Hochschild homology.
So it does not depend on the choice of a section.
If it's a sheaf.
It is a sheaf.
Yes. If F is a sheaf, then as you can see, right, the Fs UN, it doesn't really matter how you cover the set. There's no point in bothering about that. So if it's a sheaf, it's exactly the same thing you get. Now refer to this common Hochschild homology of the sheaf F on a site as simply HHN of F. Now here we have properties. So suppose that we have a short.
So you have now defined for this kind of your category with crossing topology is fixed, and now you have also a sheaf for that category, and you have defined it. How do you can you calculate the simplest possible example that sort of justifies?
If you could go with the Hochschild homology of say a point, for instance, a constant sheaf rather, that would be trivial. That would be trivial.
Okay,
but
for instance, take for instance affine space with some interesting topology like say a tile topology and choose some sheaf. Can you possibly say something interesting?
Oh, that has to be calculated. I have not done many calculations. I am mostly theoretical with things. I don't consider many examples. Okay. Whenever I give a talk, I'm everybody gets me with this question. Can you compute this? Is the universal question for getting me.
How do you compare this Hochschild with pre-existing
So I mean, this is a completely so this is working with typically with things which actually don't even have a multiplicative structure. So it's very difficult to say that. So for these objects, there isn't any such thing as an old Hochschild homology defined. So it's very difficult to say how it compares. There's nothing to compare with because it's like a module. So.
But what if you take the sheaves of Abelian groups over fixed screen or something?
So that's exactly what we.
Yeah,
but sheaves over Abelian groups do not have any ordinary definition of Hochschild homology. There's not much to compare it with.
Can you take a tensor product of these two guys and maybe?
No, but then we have the exact same problem. F tensor F. How do you go to F? There's no way. So there is no such thing as a sort of old definition. Then there's not much to compare it against. So suppose that we have a. So that is the whole point. That is the whole reason this was defined, because there is no way to do this. So suppose that we have a short exact sequence of sheaves. Now here it's a slight sort of fly in the ointment. We will require, so having a short exact sequence is not enough to give a long exact sequence. We will require it to be a short exact sequence of sheaves as well as a short exact sequence of pre-sheaves. It actually took me a while to realize that they are not both the same thing. To say that it's a short exact sequence of sheaves and a short exact sequence of pre-sheaves, because so short exact sequence of sheaves means a short exact sequence on the stalks, but that need not imply a short exact sequence at each level. So we will actually need both. Then this is sort of a small fly in the ointment. Then we have a long exact sequence like that. Then similarly, if X is a topological space and U is an open subset of X and Z is X minus U, then if we define these sheaves, so there is the there's a standard word for this kind of exact sequence, right? That is you restrict on the open set and you keep on the closed set, which supports. Then if you push forward that one, you get a long exact sequence. But there's a
localization.
Yes.
But what does this superscript E do?
Oh, E means a trivial section, 1 U to U. Because these are sheaves, so we don't really care what section we choose. Okay. So maybe I should have written the E over. I should have explained E over there. So now we will realize the importance of working with separated pre-sheaves. That is relative Hochschild homology. So suppose S and T are two sections with T less than equal to S, meaning that at every stage T of U is a refinement of S of U. So then for a pre-sheaf F, now since it's just a pre-sheaf, if it was sheaves it would be exactly the same. But if it is a separated pre-sheaf, then we can define Fs and Ft. We can define two objects, but the point is that there is a natural map, of course, from Fs to Ft, but this is now an injection. Because F is a separated pre-sheaf. If F was not a separated pre-sheaf, this would not be an injection. So the important point here is that this is definitely an injection. Now, by just taking the co-kernel, I can define a new pre-sheaf, Fs of Ft of S, T over S, and then I can construct another simplicial Abelian group which does exactly the same thing. So the thing I know is that Ft over S is a pre-sheaf on C. So I can apply to it the exact same construction. I can define the same phase maps and degeneracies which are defined in the analogous way. So I can define this object SF and T over S. So now we can define the relative Hochschild homology again as this. And now it's pretty easy to see that because we have a short exact sequence, Fs, Ft, Ft over S, and that also gives me a short exact sequence like this, and so I can apply the Hochschild homology throughout, and I will get a long exact sequence which puts the relative Hochschild homology group inside the other group. So that's how. Now as we said, we have to come back to. So we were still now working with sheaves of Abelian groups. We will work with sheaves of sets. So this is not very different. So the idea is that once again we start with a separated pre-sheaf. So again, for a covering, we define it to be a collection xi with f of ui with whatever restricts in a decent way. And then again, we have the same, we take any section and then we define this. And now instead of taking direct sum, we go with the co-product basically. So we take the co-product of that with, so again, the face maps and the degeneracies are defined in exactly the same way as we had. So now this is a simplicial set. The simplicial set, I go to its geometric realization and I take its reduced singular homology group, because that behaves perfectly with respect to long exact sequences. So define the nth Hochschild homology group to be the reduced singular homology group of this. So now now once again you can prove the exact same result. If F was a sheaf, not just a pre-sheaf, it wouldn't matter what section you took. So, and then again, if you had a relative version, you could have a relative version. That is, if you work with a now you cannot. The point is that now you cannot take a quotient. There's no such thing as a co-kernel now, of course. So you have a but you still have an injection SF to ST. The geometric realization of this immersion leads to a closed immersion of the geometric realizations. You can check that as a proof actually, and then we can define the relative Hochschild homology as the relative singular cohomology over there. So
it depends on certain coefficient of singular.
Yes. And now, so the relative version will once again fit into a long exact sequence like that, because that's just the relative singular homology group. Of course, it fits into a long exact sequence. So this gives us a long exact sequence. Now, one of the things I've always wanted to do, but I could never make sense of this, is that I hope that in some sense, if I had something like, if I had a fibration of some kind, I mean, I wanted to have some kind of analog for with sheaves for the result with abelian groups where I have a short exact sequence and it becomes a long exact sequence. So the thing is that, well, I kind of wanted to say that if I have a fibration E to B, and this is the fiber, I'm not sure of this. I want to prove. So these are some final remarks we have. That is, I want to prove this Hoc Shared Homology sequence. So these are sheaves of sets, and I have a fibration of sheaves E to B with fiber F. I mean, that is because naturally, I mean, what I would want typically is a long exact sequence like this. But I have not quite, I mean, sort of not considered completely seriously, but it's what I expect to sort of prove in the long run. And so, well, but this is a homology, so maybe it doesn't behave so well with respect to fibrations, but overall, so. Yeah, and one of the things I also wanted to do, but I didn't quite get, was I wanted to define a K-theory for sheaves in general, like this. So you have Hochschild homology. You would expect some to be able to define the K-theory, but it's not quite working out, because you can define the plus constructions, but you can't really show that the groups you are getting are abelian groups. So there's a slight problem if you want to define K-theory, and of course there is a natural question that if there is a Hochschild homology, where's the cyclic homology? But well, the cyclic homology has something to do with the cyclic nerve, so we will have to take some kind of reduced version and do it. So those are three concluding remarks one should make. So as usual we have given you a lot of time. So.
I have a few questions.
Yes.
Okay, first of all, I don't still see why you named this one as a Hochschild.
So, I mean, well, for instance, I mean, first of all, we took the sheaf and understood it as a category. Now, the standard way to define the Hochschild homology of a category is through the nerve.
Oh, that's right. Yeah,
so that's kind of a sort of already standardized version of calling what is the Hochschild homology of a category is to take the homology of its nerve. So that's kind of already there.
Yeah, but something that really confuses me is that, for instance, I mean, let's go back to the classical Hochschild homology.
Yeah.
And suppose we are dealing with the schemes, affine schemes even.
Yeah.
Then those Hochschild homologies do not satisfy localization sequence. They rather satisfy some sequence for the Jacobi whatever sequence, which is more like an extension of relation of differential form. If I have a closer variety that is embedded into, say, so y is embedded into x, then the differential forms of, say, y is embedded into x, and both of them are supposed over phi to k. Then the differential forms of k over x over k and y over k are related by certain kind of sequence. Of course,
yeah, there is that.
If it is regular embedding, but if it is not, we have something else. But the thing is, this something else is actually related to part of Hochschild homology, actually. Okay. So we actually rather have this kind of Jacobi relationship, which is not actually quite a long example.
I'm totally not familiar with this.
So for me, if it is satisfying this localization sequence, then maybe I think you found out is something different.
You really, I mean, you know, the way, well, the Hochschild homology of a category, and if you think of a category, and you think of its Hochschild homology, and if you take a ring and think of its Hochschild homology, they are in some sense two different objects.
Yeah,
I have never been able to see the two of them as the same thing.
That's right. So
So this is more or less this is basically the Hochschild homology of a fibered category. We are just calling it the Hochschild homology of a sheaf because we have understood a sheaf as a category. So this is basically, and they are really quite different objects.
Yeah,
but the thing is that they are both called Hochschild homology.
They live in different
Yes,
worlds.
they really
They
are two
totally
different objects.
unrelated.
Yes, they are two kind of different
Philosophically,
objects.
I'm just a little bit concerned because I'm not saying that the theory is wrong, but the theory, I'm probably a little concerned if the name is probably.
Well, but that is also well approved to be Hochschild homology of the category. That's totally approved.
So another concern that I have is some kind of homotopy invariance kind of thing. Like for instance, homotopy invariance is not generally desirable for Hochschild homology. Rather, we want to have a Morita invariance. And so in a sense, Morita invariance can be seen as a non-commutative version of A1 homotopy. But localization sequence is actually very, very close friend of A1 homotopy, which is actually not supposed to be true.
But if you think about it, what exactly is homotopy invariance for that sheaf? How would you formulate it? How would you formulate it?
For the even simplest possible topological case, if we have a localization sequence, the localization sequence generally comes from homotopy invariance. If you can prove homotopy invariance in general, you can actually prove under certain assumptions this localization. That's actually some.
Well, we have to keep in mind that the Hochschild homology of a category is also not a particularly. From the ring, if you think of the ring somehow as a category, I really don't see how the Hochschild homology of the category would be related to the original Hochschild homology of the ring.
That's actually making me very concerned, right? Because, for instance, Morita invariance is different from homotopy invariance. Because, for instance, if you take the, say, ring B, probably non-commutative division ring, suppose we take matrices over D, then Morita invariance say that the Hochschild homology of D is the same as Hochschild homology of the
matrix ring.
Matrices. Now, but if we have this Hochschild homology that is actually homotopy invariance, then the disaster we actually get is that we are basically just killing all of the strictures of the ring, which is sort of different from this Morita invariance.
I still don't see how they are sort of in the same part of the. They are really not very comparable. They are not. It's sort of different objects. What I am thinking of as Hochschild homology, this is a little different because I presented this talk in Vanderbilt as well. But I got some suggestions such as this is exactly speaking, strictly speaking, this is a Tor, and this is pretty much supposed to be the Hochschild homology is definitely supposed to be a Tor, as you know well. Yes. There is a way, and they showed me a very fancy category theoretic way of describing this construction as a Tor. So which it sort of satisfies Hochschild homology they had. So, but it definitely is a sort of.
So you might probably have some concrete candidates for cyclic.
There is like an obvious candidate. That is, you could work with the cyclic nerve instead of the ordinary nerve. But the description of the cyclic nerve in this particular case, I am very unhappy with its description. It looks to me a very sort of intransigent kind of object. It doesn't look like an object that is any because you are supposed to. So how does it work? So you have these xi n minus 1, all of them here. So you take the xi n, you pull it back here, pull it back here, pull it back here, it goes back to xi 0. Now what should happen in the cyclic nerve? There is another map like this, and this xi 0 is kind of supposed to come back to xi n. Somehow that doesn't look to me like something that makes a lot of sense. One could definitely define the cyclic homology, but I kind of haven't stopped short of defining it for sort of aesthetic reasons. I'm really dissatisfied with the cyclic nerve of this object. So, because it seems to be very counterintuitive to start with sections and then you keep pulling them back, and somehow after a while the pullback comes back to the same object. Kind of fail to see it how it looks like inside a sheaf. So, kind of object to the cyclic nerve of this. I take some kind of moral objection to the cyclic nerve of this object, but of course it's there, and you could define one and take periodicity sequence and everything.
So was this result already published?
No, it's submitted and it's inside the black hole. Okay. It's inside somebody's computer in some part of the world.
Okay. very good.
Thank you. So thank you for inviting me in general.